Thanks, Margot. Okay, yeah, so I'm going to be talking about a research project that was done in 2020 and 2021 with the, I guess, the Tabor Irrigation District, what they were called at the time. A typical scene in the spring is excess water pooling on fields. This can also occur during periods of extended precipitation. And so this excess water often leaves fields either through uncontrolled overland runoff or through controlled drainage means. And one of these controlled drainage means is subsurface tile drainage. And so while this improves the rooting zone, it has a tendency to transport sediment and nutrients along with it to adjacent receiving waterways, which can also include irrigation canals. So there are some benefits to using subsurface drainage, using tile drainage. It improves field conditions, so the soil moisture conditions allows producers to get into their fields and start working the soil earlier in the spring. It allows the improved soil moisture conditions in the rooting zone. This can also improve crop growth, allowing for different types of varieties to be grown as well. And it also can help to reduce erosion and sediment and contaminant transport that would otherwise be transported from overland runoff. So my colleagues at Alberta Agriculture had met with some of the irrigation districts just to hear some of their concerns about receiving tile water drainage into their conveyances. And some of the concerns that we heard were, number one, the irrigation water quality. So this can have implications for production and safety concerns. And there's also, as we heard earlier, concerns for increased nutrients reaching the conveyances, which encourages growth of aquatic weeds and algae. On the other hand, however, we heard that irrigation districts also have a desire to provide assistance to their producers in receiving this tile water drainage. So there's a bit of a balance there with managing tile drainage. So one of the irrigation districts that was part of this conversation was the Tabor Irrigation District. And so we worked a little bit closer with them in characterizing their tile drainage water. And so there was one particular lateral that was receiving water from 24 subsurface tile drains. And in terms of characterizing the water, this hasn't really been done before in Alberta. We know that there's been some tile drainage characterization studies in the United States. And so the initial goal here was to, as I say, help TID characterize their water just as a part of helping them with their approvals process. And so, as I mentioned, there was this one particular canal that was receiving 24 drains. And so my colleagues looked at this during dry conditions and during wet conditions, and just to see how they compare. And so sure enough, there was an increase of nitrogen proceeding downstream in this canal, particularly at the 1 kilometer and 2 kilometer locations. So my colleagues also looked at one of the actual pipelines draining into this canal, and so they looked at the inlet and the outlet and two midpoints along the canal. And so what they found was that there was an increase in nitrate, nitrite, and total dissolved phosphorus concentrations across those 4 locations. So this kind of prompted the desire to look into options for treating tile drainage water. So we know that there are different strategies on the surface to help reduce nutrient loading. So proven beneficial management practices like nutrient management plans. So those are your 4 R's. Soil conservation methods like reduced tillage, which helps with soil transport and erosion. Maintaining wetlands, which help with filtering out contaminants. And a few new technologies, including constructed wetlands, which mimic natural wetlands, and then kind of a little bit of a newer technology is denitrifying bioreactors. And so these act as kind of a passive treatment technology. They're installed underground, and there's your inlet would essentially be the end of the tile drain. They'd go through this chamber, which is filled with a carbon source, and coming out the other end, in theory, would be reduced nitrogen loads. So this is a bit of a busy picture, but this is the nitrogen cycle. So bioreactors operate on the principle of denitrification. So it's the process of transforming nitrate or converting nitrate into nitrogen gas. And this often occurs in waterlogged conditions, and it's performed by a very specific bacteria, denitrifying bacteria, which, as I mentioned, require a carbon energy source in order to convert the nitrate. So some of the different carbon sources for bioreactors. Wood chips are one of the most commonly used materials, but in the literature we have seen other agricultural sources used, such as corn stover, straw, and we've even seen things like sawdust and cardboard being used in these chambers. So, as I mentioned, there's a lot of literature about tile drainage and bioreactors that come from the United States. And these findings aren't always applicable to Alberta's specific conditions. So our question was, how would bioreactors perform in Alberta? And so specifically, we wanted to investigate the feasibility and effectiveness of bioreactors under Alberta-specific conditions using local agricultural carbon feedstocks. So specifically, we wanted to investigate how they would perform in the different climatic regions of Alberta. So we had 2 different study sites shown in the blue stars, one near Edmonton and one in the Tabor Irrigation District. And so each site had 9 bioreactors installed. And the agricultural carbon sources that we used were wood chips, as well as some agricultural sources. So we used hemp straw and barley straw. And then we also wanted to look at hydraulic retention times, and I'll get into this in a minute, but essentially the hydraulic retention time is how long the water stays within the chamber. So looking at the hydraulic retention time and how that impacts nutrient load, especially when you take into account different climates and different conditions of the growing season. So how does it compare over the spring, the summer, and the fall? So getting into a little bit more on the bioreactor design, there's more than one type of design, and the one that we used was the trench-style bioreactor. So this blue bar at the bottom shows the direction of water flow. So you have an inlet and an outlet. And so the chamber is dug, and then you install a kind of like a polyethylene rubber liner, and this helps to create an airtight chamber. And then you fill it with your carbon feedstock. And then we also have these, the water wells installed, so the inlet well where we can pump water into, the outlet well to allow water to drain. And then we have a couple of interior observation wells which allow us to take water samples and to install other instrumentation. So this just shows what those feedstocks looked like that we used. These are 1-liter bags, just to give you an idea of scale. So that was wood chips, barley straw, and hemp straw, like I mentioned. So a few pictures here, just showing the installation of the bioreactors at the Tabor Irrigation District site. So this is where they were digging the trench. And then laying down the liner, and you can see in that picture there, there's one of the interior wells being ready to be installed. And then packing the carbon feedstock within that chamber on top of that carbon or the poly lining, and installing those interior wells. So then once the carbon feedstock is installed, then the poly liner is folded back over on top, just to, like I mentioned, keep a kind of a controlled environment, a watertight environment. And then it's topped off with the topsoil. So you essentially just see these 4 water wells sticking out of the ground. And this arrow here shows the direction of water flow. This is just a close-up of one of the interior wells. So they were PVC pipe, and they had a cap on top, which allowed us to take our water samples. So this just are a couple of schematics from each of our sites. So the Crop Diversification Center North site in Edmonton is where the Edmonton site was installed. And then at the Tabor Irrigation District, just kind of on the shores there of the Fincastle Lake. So, so we had a water source for each site. The water source at Edmonton was a nearby stream and a nearby canal at the Tabor Irrigation District, and you can see kind of that white line there. That's our water source line. And so these pictures on the right just show every individual bioreactor. Like I mentioned, there were 9 of them at each site, so that allowed us to install 3 different bioreactors for each carbon feedstock. So I just wanted to show a little bit of the setup at the Tabor Irrigation District site. So this is the shed and the stock tank. So the stock tank is where the water was, where the source water ended up, where we mixed it with nitrogen fertilizer. So that's how we were able to reach our concentration and treat our bioreactors. And so within the shed there is where all of the plumbing was housed. So we had a filter in there because there's particulates that end up in the irrigation water. And then we also had a dosing pump, which the treated water was pumped into, allowed us to reach our target concentration. This is one of the inlet wells. You can see there's a little water meter there, so this allowed us to hit our hydraulic retention time. So the flow of the water was, the hydraulic retention time was dependent on the flow of the water, so we needed to be able to control that. And then just a differing perspective here, you can see at the bottom, that's our inlet well. When they weren't being downloaded, they were covered with little honey buckets to protect from the elements. And then you can see the white line there, that's our water source line. So as I mentioned, hydraulic retention time, this is kind of key to the bioreactor research. So it's like I mentioned, the average length of time that a solute would remain in the bioreactor, and it's inversely proportionate to the rate of flow. And so in theory as well, the longer the hydraulic retention time, the higher the nitrogen reduction. So we looked in the literature, and some of the ideal hydraulic retention times range from 4 hours to 12 hours. So those are the ranges that we worked with. So these are just some pictures showing in the left photo there, the fertilizer being mixed with the source water in the stock tank. And then the dosing pump there, the central picture, that's where the fertilizer or the treated water was routed to hit our target dose of 20 milligrams per liter, and then that was pumped out into the bioreactors. And then water samples were taken at the inlets and the outlets of the bioreactor, and the difference between those concentrations was what determined the amount of nitrogen reduction. So this just shows a few of the results. The left panel there is the Edmonton site, and the right panel is the TID site. I should mention that we did run into some logistical challenges at the Edmonton site in 2021, so I don't have data for that site, but essentially what this is showing is that there was nitrogen reduction if you look at the TID site on the right there, nitrogen was reduced between 2020, let me back up here. I wanted to show that there's, looking at the feedstocks, barley in green and hemp in the blue. So nitrogen was reduced. There was a higher percentage of nitrogen reduction for these two particular feedstocks. And so they had high rates of reduction in the first year. But then if you look at the second year in 2021, the rate of removal was less than in 2020. However, there was still higher performance by barley and hemp straw in that second year. And we can see too that comparing the first year of operation between Edmonton and TID, that the nitrogen removal was pretty much on par in terms of those two, barley and hemp. They had similar reduction rates. So this shows results for the TID in 2021 in terms of hydraulic retention time. So this shows the flow rate. So that lower flow rate shown in pink, it's 1 GPM or gallons per minute, but that's that would be the 10-hour hydraulic retention time. So the slower flow rate or the higher hydraulic retention time had a higher rate of nitrogen reduction, followed by the 1.5 GPM, which would have been equivalent to about 7.5 hours of retention time. And we see as well that barley and hemp slightly outperformed wood when we're looking at retention time. And at the bottom here, I don't know if you can see very well, but this is divided up by seasons, so spring, summer, and fall. And so we do see higher rates of reduction of nitrogen reduction during that summer season. So some of the things that we learned, that there was greater nitrate removal in 2020 compared to 2021, especially in the summertime. So there was peak performance in the summer, not so much in the spring and fall. As I mentioned, the lowest flow rate or the longest hydraulic retention time maximized nitrate removal. And barley straw actually showed the greatest nitrate removal performance, whereas wood chips showed the poorest performance for nitrogen removal. And this is good news because barley straw is easily sourced in southern Alberta. So essentially, what does this mean? So the primary factors in our experiment affecting nitrate removal were temperature, the bioreactor age, or how many seasons the bioreactor had been in operation for, as well as the flow rate or hydraulic retention time, and the carbon source material. So being that this is a new technology, and I don't think it's been explored very extensively in Alberta, so there's room for improvement, and future research questions might include things like what is the best material to use? Is it barley straw? Is it hemp straw? Are there other sources that might be better? As I mentioned, there's different design styles, so it doesn't necessarily need to be a trench style, but what would be the ideal size and design of a bioreactor? How long does the agricultural material last? Does it break down after 3, 4, 5, 10 years? And it would also be interesting to see how bioreactors would perform in conjunction with other beneficial management practices. So there's a lot more technical information that went into this experiment. So if you're interested in reading about that, we do have some publications available. So we have a technical report available on Open Alberta, as well as a fact sheet. And we also have a journal publication. It's open source, so freely available if you are interested in Googling that. And so I just wanted to say thank you to the Tabor Irrigation District for their partnership on this project, as well as thanks to the Canadian Agricultural Partnership and Alberta Innovates for their financial assistance, and all the current and former GOA staff who were involved in this project, as well as my co-authors on those publications, Janelle, who you heard from earlier, and Jacqueline Cohn. She's based out of our Edmonton building. So that's all I have for you. I'm a bit early, so we have time for questions.
Thank you for presenting these interesting topics. So quite interesting, actually. A few questions here, actually. The performance degradation in the subsequent years, as you mentioned, did not say anything about like what is it can be attributed to, because of the putrefaction of the material or something else. Would be nice to know. Another thing I'm surprised to see most obvious source of the carbon has not been used, like the charcoal. I don't know why. If that would give some more potential for elongated use in terms of like several seasons, and these also need to be explored further. Another thing, sorry, question getting longer. As you mentioned, that it's going to perform in the anaerobic condition. So I would expect it's going to be quite stinky, obnoxious in the area. So is the limit is going to exceed any regulatory, I don't know if there is a threshold build or not. Those are the few things, my observations, if you can answer.
Okay, so I think the first question was about the breakdown of the material.
Yes.
Okay, yeah. So we didn't have an opportunity to look at that, just because it was more of, can we even do this? It was just a very simple prototype, just to see if we could pull it off, essentially. So that's definitely a good point about how does the material last. And I know that there's some of the research shows that yes, there's a very high nitrogen removal in the first year and then reduced removal in the subsequent years. And I don't know if there's really an answer for that, but some studies have suggested maybe it comes down to replacing the material every so often. The second question, using charcoal as the carbon source. I don't know too much about that, but that's a good point. I think there might have been a few research articles using burned firewood even, which isn't exactly the same, but I don't think there was as much removal from that particular source. But we also just wanted to keep it simple, and we knew that the wood chips and the straw was easy to source. I'm not too sure where you would get charcoal from that easily. I'm kind of blanking on that, but and then the breakdown of the material and from the anaerobic conditions, but you need that waterlogged condition in order to carry out that denitrification process. But yes, when we did decommission the Seitz, and Janelle can attest to this, it was very stinky. There was a lot of bacterial decomposition that was happening, and so that's what I mean. There's kind of a balance there, because if the water stays within that chamber too long, you start getting unwanted chemical reactions rather than the denitrification. So Yes, all very good observations. Thank you.
Yeah, good. Thank you very much. Another question actually popped up in my mind. So, rather than like using that the pollutant, is it a pollutant? Or
Polyethylene liner?
No, not the liner. About the how did you like the source of the nutrient here?
Oh yes, it was a nitrogen fertilizer.
Yeah, fertilizer.
Yeah.
Like other than using this like artificially made thing, would we be able to use some of the effluent from the feedlot or something like that, which will have obviously a very high level of nitrogen?
It's a good point. I think like we used the inorganic nitrogen fertilizer just because it was a volume that we knew was contained within the nitrogen that was contained within that fertilizer. So we were able to have a better idea of the concentration that we were working with. I would guess though that with using something like manure that be more so a source of phosphorus rather than nitrogen. So I don't know if I have an answer for how it would work with using manure. Yeah.
Okay, thank you.
Yes, thank you.
Thanks for the presentation, Nicole.
Oh, thank you, Nicole.
Hey, I was curious to know if you had any thoughts around how these bioreactors perform as far as nitrogen reduction compared to like a vegetative filter strip or riparian area like Nevin was just mentioning in his presentation. Thanks.
Yeah, that's a good point. I don't, but I would guess that just because tile drainage is a subsurface a drainage mechanism, that having the bioreactor within that underground chamber and being able to filter it before it even enters the wetland, but maybe in conjunction, or not wetland, the water body, using that in conjunction maybe with a filter strip would probably be, wouldn't be a bad idea. Thank you.